Hi, my name is Priyadarshini Ramalingam and my group members is Logaperidhan Loganathan, Jayabalan Balakrishnan, Muhammad Ilham bin Muhammad Khalid and Priyanka Sukalingam. Today we are going to present about control principle project which is buck boost converter. So the abstract for this report is present a voltage tracking of DC buck boost converter. The buck boost converter is designed to tracking the output voltage with two modes of operation. This project report consists open loop control, closed loop control with the help of MATLAB software. The buck boost converter has some advantage compared to the other type of DC to DC converter. However, the non-linearity of the DC to DC buck boost converter characteristic because it is difficult to handle by using conventional methods such as open loop control principle. In order to overcome this main problem, a closed-loop control system using MATLAB software is developed. Simulations have been performed using MATLAB software and validated with software implementation. The simulation results show that the output voltage of the buck boost converter can be controlled according to the value of duty cycle. Document and component that we are using to do the project is first MATLAB software, DC voltage source, diode, MOSFET, capacitor, resistor, inductor and switch. Next is introduction. Introduction about a typical buck boost converter. The buck boost converter is a type of DC to DC converter that has an output voltage magnitude that is either greater than or less than the input voltage magnitude. It is used to step up the DC voltage similar to a transformer for DC circuit. Two different topologies are called buck boost converter. The input voltage source is connected to a solid state device. The second switch used is a diode. The diode is connected in reverse to the direction of power flow from source to a capacitor and the load, and the two are connected in parallel as shown in the figure above. That's all. Thank you.
Assalamualaikum. My name is Muhammad Ilham bin Muhammad Khalid and I will present about the methodology of our project. So the buck boost converter has a two mode of operation, which is mode 1 is switch is on and diode is off, while the second mode is when switch is off and diode is on. So firstly is the first mode, which is switch is on while diode is off. So when the switch is on, it offers zero resistance to flow of current. So when the switch is on, all the current will flow through the switch and inductor and back to the DC input source. This will lead inductor to store charge during the time the switch is on, and when the solid state switch is off, the polarity of the inductor reverses so that current flows through the load and through the diode and back to inductor. Next, while performing the analysis of a buck boost converter, we have to remind that the inductor current is continuous, and this is made possible by selecting an appropriate value of L, which is inductor. The inductor current in the steady state rises from a value with a positive slope to a maximum value during the on state, and the drop back down to the initial value with a negative slope. Therefore, the net charge of the inductor current over an complete circle is 0. We can see the example of circuit on the slide. For the second mode, which is switch is off and diode is on, the polarity of the inductor is reversed and the energy stored in the inductor is released and is ultimately dissipated in the load resistance, and this helps to maintain the flow of current in the same direction through the load and also step up the output voltage, as the inductor is now also acting as a source in conjunction with the input source. But for analysis, we keep the original conventions to analyze the circuit using KVL. We know that D varies between 0 and 1. If the D bigger than 0.5, the output voltage is larger than the input. And if D smaller than 0.5, the output is smaller than the input. But if D equal to 0.5, the output voltage is equal to the input voltage.
Hi, my name is Loga Prison. So I'm going to present about the circuit of the buck boost converter with the simulation and the outputs. So these are the circuit for the buck boost converter that we created in MATLAB using Simulink MATLAB. So first we choose the components such as DC voltage source, MOSFET, diode, inductor, capacitor, resistor, and most importantly ground. We grounded the circuit. So for the next one, so after we created the circuit, we for the output, we just inputted a voltage measurement and for pulse generator and the display to show the exact value of the voltage output from this buck boost converter. So first we set the value for DC voltage. For input value is 12 voltage, and for the inductor we choose 63 micro H for the inductor value. For the capacitor value we choose 72.5 micro F. So for the resistor value we choose 10 ohm. For where we take this value from the calculation we previously do before the circuit. So these are the calculation. For the duty ratio we do 0.29, and for the inductor current 0.69, for the minimum inductance 63 micro H, for the rate of change of inductor current 1.38 ampere, and minimum inductor current for 0 ampere, and the minimum capacitance is 72.5 microfarad. So from the calculation we took the answer and put the value into the certain components. So for the pulse generator we put the duty ratio to 0.29 in the pulse width. For the period we for the frequency we choose 40 kilohertz. So for the period we have to convert to 1 over f, so 1 over 40 kilohertz. So we put the stop time to 2 seconds. So first I run it. So as I said previously, the voltage input is 12 volt, and the output we get a negative 4.487. So because buck boost converter, this converter is an inverting DC to DC converter. For example, the polarity of the output voltage is reversed compared to the input supply. So thus it is a negative output buck boost converter. So because of that the voltage output become negative, so almost to the 5 volt the output voltage. So for the waveform voltage of waveform voltage, so we create separate circuit. So this is the circuit. So for the waveform of voltage waveform, So this is the input voltage of waveform. This is the waveform for the MOSFET, inductor, diode, capacitor, and the output voltage. These are the waveforms for the voltage. So for the next circuit for the current waveform. So these are the circuit for the current waveform. So the simulation is run ready. So for the waveform, so this is the waveform for the current. So this is the input current of waveform. This is MOSFET. This one is for the inductor, and this one is the diode, capacitor, and the output waveform. So the input waveform and the output waveform for the current. So that's all from me. Thank you.
Hi, I'm Jaya Balan. I'm here to present calculation we did for this project. Okay, let's look at the calculation. Vs equals to 12 volt, R equals to 1 percentage, V out equals to 5 volt, frequency is 40 kilohertz, R equals to 10 ohm, T equals to 1 over 40 kilohertz. So for the duty ratio we got 0.29. By using inductor current formula we got 0.69. By using minimum inductance current formula 16 we got 63 microhertz. For the rate of change of inductor current is 1.38 ampere. Then minimum inductor current we got 0 ampere. Minimum capacitance we got 72.5 microfarad. Let's move on to state space equation. So these are the equation for the state space. So the switch state space model of this power converter is this equation. So let's look at the mode 1 in boost converter during on mode. Okay, for KVL, V in minus DIL over L dt equals 0, whereas for KCL, R plus C dVc over dt equals 0. So this is the state space form. So in boost converter during off mode, for KVL, V in minus Vc minus L DIL over dt equals 0, whereas for KCL, IL minus Vc over R minus C dVc over dt equals 0. So this is the state space form. For mode 2, in buck converter during on mode, as you can see the KVL formula is slightly different if you compare with the boost converter. Okay, for KVL equation is V in minus L DIL over dt minus Vc equals 0, whereas for KCL, Vc over R plus C dVc over dt minus IL equals 0. So for state space form, these are the formula. So in buck converter during off mode, from KVL is Vc plus L DIL over dt equals 0. For KCL, IL minus Vc over R minus C dVc over dt equals 0. So this is the state space form. So let's move on to the state space average. For on mode, x equals to a1x plus b1 v in, whereas for off mode, x equals to a2x plus b2 v in. So with this correction vector, the average modified model becomes this form. So for buck converter is like this. For state space average model, equation is this. For boost converter, the equation is this, and then the state space average is this. These are the equations we use for this project. That's all from me. Thank you.
So I would like to talk about discussion conclusion. Okay, like the buck and boost converters, the operation of the buck boost is the best understood in terms of the inductor's reluctance to allow rapid change in current. From the initial state in which nothing is charged and the switch is open, the current through the inductor is zero. When the switch is first closed, the blocking diode prevents current from the flowing into the right hand side of the circuit, so it must all flow through the inductor. However, since the inductor doesn't allow rapid current change, it will initially keep the current low by dropping most of the voltage provided the source. Over time, the inductor will allow the current to slowly increase by decreasing its own resistance, and in an ideal circuit, the voltage drop across the inductor would remain constant. When the inherited resistance of the wires and the switch is taken into account, then the voltage drop across the inductor will also decrease as the current is increases. Also, during this time, the inductor will store energy in the form of a negative field. So let me continue on conclusion. In the end of the experiment, we have learned about how to analyze the impact of input voltage, load current, and inductance on the continuous, either discontinuous operation mode. Continuous inductor current mode is characterized by current flowing continuously in the inductor during the entire switching cycle in steady state operation. Discontinuous inductor current mode is characterized by the inductor current being zero for a portion of the switching cycle. Lastly, we have learned about the operation of the circuit that will be operated under CM and open loop conditions. An open loop system is a type of control system in which the output of the system depends on the input, but the input or the controller is independent of the output of the system. These systems do not contain any feedback loop and thus are also known as non-feedback system. Moving up on the next. Okay, this will be our Gantt chart that as you can see, role group members, which is as a project leader, engineer 1 until engineer 4. Okay, I would like to thank you to all members and this is our will be our contribution. Okay, Loga Pridhan, behalf on the circuit and simulation result, Jay Balan for calculation slide and video editor, Priya Tarshini introduction, abstract and equipments, Priyanka me as discussion conclusion, and lastly Ilham for the methodology. So that's all from us. Thank you so much.